So today we're going to talk about electron configurations. I'm hoping this will be easier for you because we've done quantum numbers. Here's the quantum numbers that you've already learned. N equals 1, N equals 2, 3, and 4. One of the things I want to point out to you is if you look at these quantum numbers and you think about them in increasing energy, N equals 1 has less energy than N equals 2. And remember when we talked about the Bohr models and he was talking about the rings and the electrons jumping from one ring to the next ring. So this should come as no surprise to you that the first energy level has less energy than the second energy level. But I have a periodic table out here because I want to show you why some kind of funky stuff happens. The N equals 4s energy level has less energy than the 3d energy level. And this might be confusing if you're asked a question, which one has more energy? But if we look at our periodic table here, we can see that 4s is right here, and it's going to come before 3D if we count from calcium number 20 to scantium number 21. So that should come as really no surprise to you if you're thinking about what we've already learned for quantum numbers. So the first thing we're going to do is we're going to diagram these electron configurations. There's some basic rules here, okay? Always fill in from the lowest energy up. That's what we just were talking about. You're going to use arrows to represent electrons, okay? The first electron in all orbitals points up. Couple notes about the way I draw arrows. Sometimes I draw an arrow like that, and sometimes I'm lazy and I draw an arrow like that. Those are the same thing when we talk about arrows. When filling electrons into sublevels with multiple orbitals, put one electron into each orbital before pairing them. Now, if you've got yourself pretty good and confused there, that's okay, because I'm going to run through a lot of examples of these that will hopefully make more sense to you. All right. The Pauli exclusion principle and Hund's rule guide us in the aufbau process, right? I wrote because I'm sure you're probably wondering what I'm talking about. Okay, so we'll come back to these, but Pauli said that no two electrons can have the same four quantum numbers. And that makes sense because when you go to the periodic table, if you look around the periodic table, if you were looking for the four quantum numbers example for ruthenium, they would be just ruthenium and nothing else. So that's the very first thing that Pauli said. The second thing was a guy named Hund, and it says electrons fill each and all orbitals in the subshell before they pair up with opposite spins. And this one I'm going to show you a couple different ways. And then finally, the aufbau process is just the filling order of the orbitals. Okay, this is what we're doing to work out the electron diagrams and the electron configurations. So nothing really special here other than the aufbau process is just how we're going to fill this all. So this is an entire electron diagram. I don't expect you to memorize this because you have a periodic table at your disposal. Okay, so when we read the periodic table, we are going to be reading the periodic table from left to right. I like to tell students, you read it like a book. You start here and you read, and then you read, you keep reading, and you keep reading, and you read it like a book. The only exception is that when you get to here, you have to remember to jump down in your book and come here and then come back there. So please, as we're going through this, don't be trying to memorize any of this. Instead, be using your periodic table for everything. So if you look here, it says we go 1s, right? Look at your periodic table, 1s comes, and then 2s, 2p, 3s, 3p, 3s, and I highlighted this because it's weird, 3d, 4p, 5s, 4d, right? So again, periodic table, 1s, 2s, 2p is over here, 3s, 3p is over here, 4s, and then it turns into 3D, 3Ds. These are the 3Ds. And then back to the 4Ps. 5s, right here, 5s. 4D is right here. This is the 4D. And then to 5p. Now I know this is kind of painful to think about, but I think if you learn how to read the periodic table, it makes a lot of sense. So here is a diagram. This is what I mean when I say diagram. Here's an example. Lithium, if we look over here on this side, this is lithium. Lithium is located in the 2s sublevel. So when we do a diagram for lithium, it looks like this. There's hydrogen, helium, lithium. All right, so lithium contains hydrogen's electron, helium's electron, and lithium's electron. Remember at the very beginning of this chapter, I told you that they contain all of the electrons that come before them. So lithium would contain hydrogen, helium, and lithium's electrons. So that's a pretty easy diagram, pretty short. Here is sulfur, a little bit larger, right? So first, let's work it out over here. You're going to have the 1s is going to be filled with hydrogen and helium. Hydrogen and helium. And then we've got lithium, beryllium, lithium, beryllium. And then we go over here to boron, carbon, nitrogen, oxygen, fluorine, neon. So let me show you those. Over here, boron spins up, carbon spins up, nitrogen spins up, oxygen, fluorine, neon. 3s, sodium, magnesium, sodium, magnesium. And then we've got to make it all the way over to sulfur. So aluminum, silicon, phosphorus, sulfur. Aluminum spins up, silicon spins up, phosphorus spins up, and there's sulfur. Now you might be asking yourself, Mrs. Robles, when you got all done with this, you just ended up filling up everything before it. And then this was really the only one I had to worry about. And yes, I completely agree with you. And don't worry, we will be getting into ways to shorten these. But for now, we've got to diagram the entire thing. This entire process right here, this is the aufbau process, right? The aufbau process is the order in which we fill them. We start with the lowest energy and then we work our way up. And then the second thing is Hund's rule tells me that I'm going to fill up, up, up before I move to the downspin, downspin, downspin. That's Hund's rule. And then lastly, the Pauli exclusion principle says that I'm never going to have an upspinning electron and then another upspinning electron. That just would not happen. So let's look at some more examples. This one is a little bit further down the periodic table, all the way to manganese. Here's manganese right here. Manganese, looking ahead, is going to be in the 3D sublevel. So again, hydrogen, helium, lithium, beryllium. Now watch me fill this up, up, up. Okay, that's Hund's rule. Down, down, down. It is not a good habit to get into to do this. Up, down, up, down. That's just like so bad of a habit that I don't want you to ever do it there, because what I'm looking at is I'm looking at 3p, aluminum, silicon, phosphorus. Aluminum, silicon, phosphorus are right there. And then sulfur, chlorine, and argon spin down. Sulfur, chlorine, and argon. Sorry that I went in a different color there. So 4s spins up and then down. And then to make it to manganese, we're going to go scandium, titanium, vanadium, chromium, and manganese. So this is the electron configuration diagram for manganese. And at the end of the day, we can see that we have 5 up spinning electrons, which is going to give us some very interesting chemistry someday. Now, drawing them like that from bottom to top gets to be kind of pesky. So instead, chemists will draw them out in a line like this. All right. It's literally the exact same thing as before. So here we're looking at chlorine. And so chlorine is right here, number 17. And we're going to fill 1s, hydrogen, helium, lithium, beryllium, boron, up, carbon, up, nitrogen, oxygen, fluorine, neon. Working my way down, I'm here. Sodium, magnesium, and then I've got to go aluminum, silicon, phosphorus, sulfur, and there's chlorine. So that's the electron configuration diagram for chlorine. These are kind of fun. These are fill in what you think these are. All right, there's a couple different ways you can do this, but what I like to do is I like to look and make sure everything is filled up properly, up, down, up, down, up, down, up, down. Okay, so we followed Hund's rule and Pauli exclusion principle, and we're going in the aufbau process, and I like to look here at 3p, and I like to see there are 2 electrons in the 3p sublevel. So 3p is right here. Here's the 3p sublevel, and if I have 2 electrons, that's going to give me silicon. Aluminum has 1 electron, silicon has 2 electrons. So this is a diagram for silicon. Looking here, this is now the 2p sublevel, and the 2p sublevel goes up, 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 down, down. So it has 5 total electrons. Over here, 2p, 1, 2, 3, 4, 5. This ends up being fluorine. And then the last one has a full 3s sublevel here. And so 3s being full is going to end up being magnesium. So make sure if I went too quickly on those, you take out your periodic table and take a look. This diagram is particularly helpful. I think everyone should make sure that they have this diagram somewhere easy to locate, right? This has everything. It has your energy levels. It shows you that the 3Ds are here, the 4Ds, the 5Ds. It even shows you that this is technically period 6, but it's a 4F. I like these. It shows you the S, P, D, and F blocks. It has them colored. So it's good to kind of keep those somewhere. All right, moving on. So we did the diagrams. Now we need to do the actual electron configurations. The electron configurations are going to tell us what sublevels contain which electrons. And it tells us this with a subscript. So if you'll remember, we would have gone 1s, and we would have shown 1 arrow here for hydrogen, and then we would have shown 2 arrows for helium. Well, instead, we can just write 1, this superscript here, sorry, not subscript. This superscript means you have 1 arrow in there, or 1 electron, and this one means you have 2. I get a lot of students that'll call this 1s squared, and I can tell that they didn't watch any notes or learn anything, because this is not 1s squared, this is 1s2. And this is what it would look like in a diagram. Lithium, again, if I go to my periodic table here, I can see lithium pretty easily. I've got 1s1, 1s2, and then I go 2s1. So 1s2, 2s1. Sodium is down here. Here's sodium. So I'm going to go through the 1s2s, 2s2 is full, 2p6 is full, and I'm going to end with the 3s1. So it's exactly the same as the diagrams. I can just write it shorter. So here's hydrogen. Hydrogen is 1s1. That means it's in the first period. of the S block in the first column of the S block. All right, so these get pretty fun. We can do beryllium, right? So looking ahead here, beryllium is right here. If you'd like to think about what you're going to write for beryllium, they all kind of start the same. 1s2, 2s2, right? Phosphorus. Phosphorus is where's phosphorus? Way over here. So we've got to go through the 1s2, 2s2, 2p6, 3s2, and 3p3. So that's how we end up with phosphorus. Now, at this point, you're probably wondering, what is the point of all of this? I promise there is a point in chemistry. Let's do zinc. Zinc is way over here, so we're going to end somewhere in the 3D sublevel. But before we get to 3D, we have to read all the rest of them out. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then don't forget, right here, it starts 3D, and we're going to go all the way to 3D10 is what we end up with there to get to zinc. So a couple more of them. We could do these all day long, and you're probably wondering, how many of these do I have to do? Well, you'll get plenty of practice. Here's krypton. Krypton is way over at the other side of the periodic table by the noble gases. So we're going to go through the 1s2s, 2s2, 2p6, 3s2, 3p6, 4s2, 3D10, that gets confusing every time, and back to 4S all the way, or 4P6. And I apologize if I misspeak any of these. It gets to be kind of tongue twisterous after a while. And there's bismuth, must be way down on the periodic table because I can see that electron configuration diagram is, goes all the way to 6p3. Bismuth here, and I'll run through this just kind of once with you. I'm going to change my color. I'm kind of getting sick of the green there, right? 1s1. Remember to read all the way to 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 starts the 3d10, 4p6, 5s2. By the way, I'm here. Hopefully you're reading along with me if you haven't fallen asleep by now. 4d10 is right there. Sorry, my pen has literally died. So 4d10, 5p6, 5s2, for F14, I had to come down, way down here to 4F14, and then back up to 5D10. That starts with hafnium there, 26P3. I apologize. These get really long. It's probably better for you to just kind of match them up and work them out anyways. All right, that's about it. There's a lot of practice with this. Remember to read your periodic table like a book and to follow what we originally did, which was way back at the beginning, to make sure that you're following the energy levels from lowest energy level to highest energy level.